we're going to be understanding in terms of change over time is soils. So for today, I want to walk you through the nuts and bolts of how this project came to be, because I think that that's instructive in understanding the kinds of questions we can answer with this effort. And I'd wager, and I'd like to offer up the idea to the audience that this effort will result in, I think, if successful, the largest extent spatially, as well as temporally back in time, of any soil archive in the world. And I think we have Rothamsted beat out in terms of the spatial extent. More importantly, I think for research and for basic agronomic implications, there's a lot that we can do with this archive set. So with that, I want to just jump right into it. This is a project that's funded in part largely by NREC, and there's also other supporting funders here that have supported through, say, finding sites like ISA has been very helpful for this, as well as funding seed money like the U of I, or helping us contact farmers like Farm Bureau again. So, and of course, I want to acknowledge the team that makes this happen. These are the 7 team members that are in the long-term soil change theme of our lab. We have different themes within our group, and this is one that features the archive you're about to hear. So I want to begin with this quote by Henry Jansen, who is a very interesting soil scientist in Canada. He's got some great work. Whenever he drops a paper, it's once every few years. It's a total headbanger of a paper. It's very good stuff. And one of my very favorite papers by Henry Jansen is this one, or it at least has this quote about soils. And the idea is that there's something deeper from soil science that we can understand about changes in the land and the continuum of time. It goes beyond a few generations. This might be a little bit philosophical, but I think it's a good place to start. We've all learned in pedology that as you go deeper in the soil, you're going back in time. You get older layers as you go deeper. And so in some sense, soils act as a living memory bank, of changes. So great paper entitled "The Soil Remembers" by Henry Jansen. And a good example of this in real life would be that of the state surveys. So this is one of my other favorite quotes that was uttered by the former director of the state survey for Illinois in 1928, Dr. R.S. Smith. And what he's getting at is that at the time, what they were focusing on was mapping soils. The fact that on your smartphone you have an app that tells you the soil type that you're sitting on is remarkable. I've worked in the developing world. There's no soil maps. They're very poorly done. You don't have that information at your fingertips, literally speaking, like we do. And that has all been the result of an effort that's been going on since the late 1800s, even the 1890s. So the soil survey, I think, began in the first states of California and in Illinois in 1899, and it began in Illinois in Adams County in that year. And at first it was a state effort. There was no NRCS. There wasn't even SCS yet. That came later on post the Dust Bowl. So at first there's no federal cooperative survey. It was simply state by state, even county by county. And the objective here was, even before soil taxonomy was a thing, to understand soils based on morphology and color. Are they timber soils? Are they yellow timber soils? Are they black prairie soils, etc.? And this effort, again, kicked off in 1899. It was done, obviously, by U of I with scientists that we know, like not just Guy Smith, but also Cyril Hopkins. And part of this was really focusing on nutrients. There was mapping of soils to understand, as you can see right here, their morphological classification, which is often like the Chinese system today, right? It's color-based. You got, in their system, purple soils, for example. Well, back then it was a mixture of native vegetation, texture, and color that dictated the classification. Again, there was no USD soil taxonomy. Drummer, Flanagan series were not yet a thing. And note that there's a big emphasis when they were mapping soils at the turn of the century on fertility. What is, quote, plant food, as they would say. And they're looking at nutrient stocks as part of their mapping of soil. So it was less pedology and more fertility mapping when it began in Illinois. Now, these samples were collected officially as part of state survey in 1899, from what I can gather, but there were some samples taken before that by the Geological Survey. And the oldest sample that we found in the archive on campus is this one here from 1861. This is a photo of it. Looks like it's ink quill pen. Maybe this was rewritten. And I've transcribed the label here. This is from the IGS from Perry County. It gives you the location, more or less. And then it says virgin prairie soil. So the prairies were pretty much on their way out by the 1880s, 1850s. So this is probably the last virgin prairie soil that existed, or let's say soils under native prairie. This blows my mind. We have a sample here that was sampled at the time when Abraham Lincoln was president. The Civil War is breaking out. It's a pretty cool time capsule. Now, I got this soil from this location. This is one of the storage barns on campus that these soils have flitted to. They used to be in Davenport Hall on the main quad. Then they were put in the tunnels that were beneath the quad, and they went to Turner Hall. Then they went to South Campus here, as best as I can reconstruct the history. And so some of these jars go back to 1860. Some of these jars have been smashed because the barn is falling apart. And this is a collection of marl plot soils from 1904 to present day, as well as the state survey that I just mentioned. Now, I want to mention that a lot of this work was initiated by Dr. Ted Peck. For those that don't know, he was a soil faculty member in our department. He passed away in 2003, and the work pretty much died with him. So there's a photo of Dr. Peck. I never met the man, wish I could. And he began the process of curating and organizing these soils. So when we came upon this barn that was in a state of collapse, what we were discovering, really, it was a rediscovery of what Ted Peck realized was a really valuable resource. And so note that he even mentions 1876 in this article. That's really the marl plots. So this article was a year before he passed, unfortunately. Now, when we go through these samples, to give you some more information to set up the value of them, there's labels on the outside, which, as you can kind of make out, they say the horizon. These are genetic layers. They're not fixed steps. The date of sampling, the county. Sometimes they have the township and the sectionship. And then as they get more recent, they have latitude and longitude. And the key thing is that, one, that's valuable information, you know when and where. And second, if you look at the inside of the jars, they have a pretty well preserved card. These are sieve soils, they're air dried. I'm amazed that they didn't decompose, but they haven't. So we can use the preserved label on the inside to understand these soils, where they're from. Here are just some more examples. You can make out the really nice emphasis on the horizons, including the depth of sampling. And in some cases, they are now using the series names that we all know, like Muscatine, Muscatoon. I know there's a big, that there is a misunderstanding of those, but some of these series are no longer in existence. The point, though, is that we can track now the NRCS Kellogg Soil Survey Lab classifications. And so here's another example of how we can link some of these soils to the NRCS data sets and Web Soil Survey. Here's one example. The code on these jars in this example are the same 5-numbered code as what you find for the PEDON layer identifier in the NCSS database of NRCS. So this is great because we have data and we have got the original PEDONs being used to classify these soils. Okay, well, in some cases we have to be a little bit more creative. So here's one example. Soils that were really pre-1980 don't have latitude and longitude, but they've got the old school survey approach where you've got the township, the section. Now this is still leaving a pretty big area. It's an entire section. So we've got the center point of that if we translate it, but we still have to make some decisions on where to sample if we wanted to say resample where someone took the original soil. So for this, we can use modern soil survey maps to at least winnow down. In this example, this is the Douglas Silt Loam, and we've got the Douglas Silt Loam as 128. There's a few locations within the section that helps us narrow where we sampled to compare. And this is important because if we sample this site, in this example last year, it was originally taken in 1965, that effectively is a delta of time of 56 years. Now, because we have these PEDONs across the state and going back to the 1800s, we can have a chronosequence, a delta in time, that goes back from as recently as 5 years to going back to 120 years. So that's pretty powerful. We also had to go up to Nebraska. Last March, we drove up with the van to repatriate soils that were taken in the second half of the 20th century. Shown here is the NRCS KSSL archives. We took about 800 samples back from there. Now we finished the work that Ted Peck sought out to do, where we've reorganized by county every single pedon sample taken, as far as we know, as part of the state survey, and then as part of cooperative federal survey in the second half of the 20th century. This then is the spatial and the temporal extents of the archive of pedons, left and right hand. So we've got on the left hand the exact sampling locations. On the right hand side, we have the temporal spread of the pedons. So we do have some more pedons that predate 1920. They're not shown here. There's few of them and they're somewhat incomplete, but we easily have a 100-year chronosequence, full pedon scale. And when I say pedon, just so we're clear, we're not talking surface depth, we're talking genetic horizons down to 3, sometimes 5 foot depth. So why does this matter? What does this mean? I want to give some context for the age of soils. This is from a paper that we published with USDA colleagues. We did a meta-analysis of the average age of soil archive collections. So the first thing to note is that the median and mean age is roughly 37 to 48 years. So we're less than half a century. Rothamsted, which is the oldest continuous long-term trial or trials in the world, they obviously are the oldest. This is at the time of study in 2020, the meta-analysis. But the pedon collection that we have, it's not from a field trial. So unlike these other studies that are largely less than half a century, and they're place-based, like the Mara plots, they're a field, we have a huge spatial extent that goes back 100 to 120 years. For reference, the Mara plots on this diagram would map back here, and the oldest sample that you just saw from the Civil War era would date back to, or rather ties with the oldest Rothamsted sample. So this is valuable because by resampling, we can effectively construct a chronosequence. Now, I want to give 3 examples of how we might use this information, and then talk about how we could use your help if you have interest in being part of this work. So the first example is that we can understand basic changes in soils over time. And a good example of this comes to us from Iowa State, where there is a paper published by Veenstra, and in this work, she looked at a 57-year pairwise comparison. So basically looking at soils, really pedons, that were profiled by NRCS in the 1960s at the time of sampling. And so then they resampled it and they were able to understand how things have changed over time. Sorry, I'm going to mute someone. I'm getting a lot of background noise. There we go. Okay. And what you can do in this example is by comparing the delta of 57 years, in their example, it's a morphological or a pedological evaluation across 82 locations. So what they found, for example, was that you tend to get erosional effects where you get thinner topsoils on the back slopes where things are eroding, and then you get where that soil eroded to, you get a cumulic horizon on the toe slope. So basically what they found was that you're losing a few inches on the back slopes and it's building up on the toe slope as eroded soil. Erosion is not a soil loss, right? It's simply a transfer of soil down the landscape. They also found things like increased depth of molic colors, which is interesting. It means that you've got more organic matter, presumably to greater depth. There was a loss, though, of the granular structure that one often sees under native prairie, which makes sense. There is a downward migration of the gray redox features, which is consistent with more tile drainage, lowering the water table. And there is a greater drop in pH, or there is a drop in pH, excuse me, relative to the 1950s, 1960s comparison. So our soils are eroding, they are having more organic matter, they're better drained, and they're more acidic. They are lower pH. This is what they were able to conclude. This is valuable because it raises some questions like, is it really drummer if we've tile drained a drummer? A drummer by definition has a seasonal saturation about 2 feet down. Well, if you tile drain a drummer, it's not really drummer, it's more like a Flanagan. That's a little bit nerdy. It's a classification emphasis, but there's implications here for things like carbon storage, nutrient leaching if we're changing the soil type by virtue of subsurface saturation. So in our case, here's an example of how we can do this with a chronosequence approach. This is from the Morrow plots. We do have these also in the archive. We know that they were sampled beginning in 1904. We have those soils in our archive. We're in the process of looking at them. And this is a photo of the first soil sampling in 04. You might ask, why did they begin to sample in 1904 first? Well, that's when they begin to implement fertility treatments. So from its inception in 1876 until 1904, in those first roughly 30 or 28 years, the Morrow plots were simply crop rotation treatments. There was no fertility treatments yet. And when they began those treatments in 04, they had the wisdom to, one, sample soils as baseline, and two, to archive those. And so about 100 and, well, let's do some math here. About 119 years later, we can resample these soils. And by subtracting the time that has elapsed, we get a chronosequence. And these are actually cores that you're seeing from the different Morrow plot treatments. And you can make out some differences in the depth of the A horizon. That's an example of the chronosequence approach. And the application here is to understand things like A horizon thickness. And that is, again, shown here for the Morrow plots and for the Iowa State study. But we're hoping to do this across the state of Illinois using this comprehensive collection of pedons. So that's one example. The second example would be the very applied use of this to look at legacy phosphorus and to look at just native phosphorus stocks. The latter is important because we know that there wasn't really much P input. There was a bit of phosphate rock in about 1940 on the bottom left graph. And that kind of fizzled out, and we had soluble P inputs beginning with triple or single super. That was quickly supplanted by DAP and MAP by the 1960s. But we do have pedons that predate any P usage, which means that by quantifying P stocks in these different layers of each pedon, we can understand indigenous soil phosphorus stocks. The same can be said of potassium, carbon, etc. That's pretty powerful. And here's an example of how we can understand or use this in a few ways. What you're seeing here is, I think, the first phosphorus map of the state ever. This is down to 60-inch depth, 5-foot depth. And we did this by analyzing the pedons pre-1950 without any influence of phosphorus inputs. And you can make out that there's quite a bit of variation across the state. And as we'll see in a second, there's implications for basic agronomic recommendations like the subsoil P supply power concept that's in our state's agronomy handbook. Now, the important thing here is that we can use this for things like legacy phosphorus, which, to give you a quick working definition, is phosphorus that was applied and not used by the crop. That could have been 1 year ago, it could have been 100 years ago. Usually we mean it to mean many years ago. It's residual phosphorus at the long term. And we know from previous studies, like this one by Dr. Mark David, when he was still at U of I, that if we reanalyze his data, like I've done here by shading the area beneath the curve of net inputs, the area in green would be the amount of phosphorus, if you integrate that area, that has been added and not used by the crop. And so if you do the math on that, it's roughly 5 billion pounds of phosphorus that are legacy P across the state. But one, we don't know if that's true. This is based on a mass balance. And number two, we don't know where it is across the state. And quantifying those two things is important because, one, you actually need to do a stock, a delta in the stock to verify a balance, right? Balance is on paper, a stock delta is by resampling, like we can do with this archive, to verify the balance. And second, we can know where it is and what watershed. That's important because not only can we account for the amount of legacy P, we might be able to help link changes in phosphorus export from the state into the Mississippi River Basin by identifying hotspots of legacy phosphorus. Legacy P is thought to be responsible in part for the slow release of P to waterways. So this is important because there's a clear water quality insight that we can derive from understanding the where of legacy P if we resample these same locations. So this is where the resampling chronosequence approach is quite critical. If we go back to that of soil fertility, there's also some very good applied things that we can do, still on the topic of phosphorus. This, as I mentioned, is the first phosphorus map of Illinois. It's to depth. This is total phosphorus. And we think it's the most detailed map in the world, defined by spatial resolution and depth. There's models of global P stocks to the top 50 centimeters. Here we're going 3 times that depth with actual measurements, not models. Why does this matter? Well, one is that it's useful to understand fine scale variability, I think. And second, we can try to link this with geological influences like the recency of glaciation and the parent materials across the state. And this is an example of why this matters for fertility. In the chapter 8 of the Illinois Agronomy Handbook, we see this map here on the right-hand side, where they propose different regions of soil P supply power. You've got high, medium, and low. This is predicated on 3 things. One is the thickness of the loess, as you can see here, the age and thus the P content of the loess, and third would be the drainage. That last one doesn't make sense now that we tile drain things quite extensively. But what you can do is by comparing the actual measured P stock map that we have derived from this archive on the left with the subsoil P supply content on the right, well, the P content accounts for the loess thickness and depth. So we should be able to verify, is this map from the handbook on the right-hand side actually, well, how accurate is it? And in some cases, like shown here, we get pretty good verification. So the circles in green on both maps show that there's agreement that these are high on the west and low on the east part of the state supply power regions. But if you look at some other areas, like these 3 shown in red, there's some regions where there's discrepancies. So for example, in central Illinois around Decatur, the middle red circle, it's charted as mediums, but it's actually the lowest spot, in fact, of the state's P stocks. And conversely, down south in that southern circle, that's mapped as low, but we see there's actually quite high P stocks. So there are some discrepancies. These are just 3 examples of how we can use these maps, especially if we resample these locations. So you might imagine there's all kinds of questions that we can answer. There's things like carbon stocks, carbon deficits versus saturation, looking at K stocks, looking at lead deposition from coal burning as a signature of atmospheric deposition in general, and thus sulfur deposition. One that we're partnering with some engineers on campus to address right now is looking at radionuclide signals from beryllium-10 and cesium-137. These are radionuclides that were dusted across the US after the nuclear weapons testing in New Mexico in the 1950s. And because there's a known signal of deposition of cesium-137 and beryllium-10, we can, based on the leaching rates of that and knowing the surface deposition time point, we can infer erosion rates since 1950. So we can look at erosion by the A-horizon truncation. A complementary approach would be the radionuclide signal. These are just examples of how we can learn a lot about our soil resource base and do applied research like fertility maps. So I want to end this with a request for your help. We have, as shown here by the QR code, which will link you to the Google map on the left-hand side, we have identified 453 locations that have pedons that are well characterized, meaning we have all the horizons to 3-foot depth or more. We know when they were sampled, we know where they were sampled, either within the section or even the lat and longitude. And we're in the process this springtime of sampling about 45 of these locations. That's 10%. We've only been able to track down landowner contacts for about 100. And of course, we have to ask for permission. So the message here is that if you know of anybody who farms and or owns a given location where these pins fall into, we would be really appreciative of any leads and any contacts, especially if there's a relationship that you have with someone, there's some trust there. So we don't want to just be blind or cold calling people. We'd like to approach them through a relationship if possible. What we would give in exchange is obviously all the data for that person, for their site. We would be taking 6 to 7 Giddings probe cores, so pretty small sampling footprint. We're not tearing up a field to do a pit. And we would scrub the exact location from the data set. It would be anonymized and hosted on U of I servers to protect privacy. And we would never show point data. We would show up with these maps like you just saw for on the left-hand side here. This is a map made by Cregan. You can't identify the original location at the field scale. So with that, I think we've got time for questions. I intentionally tried to give a shorter 30 minutes so that we can discuss and be happy to get your thoughts. Thanks, folks. Thanks, Jim.
Guys, happy to open it up to any questions that someone might have, or let's type stuff in the chat if you have questions. We'll give it a few minutes, and if there are no questions, we can just assume people will follow up with you via email.
Loved all the old photos, Andrew. Where'd you find all those?
Thanks, Gary. Which one? Sorry, of the soils or of the Mara plot sampling?
The old barn, the old samples. I mean, that's just, you just went out and got those, or those in archives somewhere?
Well, they're now finally archived. So the backstory here is my department head said, hey, there's a barn that is scheduled for demolition. The location of the barn here is about half a kilometer to the west, 500 yards from the Vet Med Center. It's by the old agronomy house, seed house, on the edge of the South Farms. So just north of Windsor Road. It's right next to Fred Belo's lab, actually, down on South Farms. And so that's what you're seeing here. There's a few of the beams actually blew off and hit Fred's truck and damaged the truck. So it was a human health risk, obviously. And so I went in there in August of 2018 with the headlamp just to check it out. I'm always into soils, and came out 6 hours later because I couldn't tear myself away from the jars. It's exciting, right? It's almost like I don't know, a box of chocolates. Every jar is unique and you don't know how old it is. So that's how it happened, Gary, the actual discovery, or let's say the rediscovery. Like a lot of things, when someone who is the lead on something passes, the knowledge dies with them. And that happened with Ted Peck. So we finished the job that he began. We spent 2 years going jar by jar in the shed. This is basically I'd say maybe 4,000 square foot. It's pretty big. There were over 10,000 jars. Some were in piles. We had to go through them. We made a digital scan of every single label. We had to reorganize it. So now we finally have done that work, and we've reorganized them in a different pole barn on campus, which is the one, let's see if I've got a photo shown here. So we've got an infrastructure that actually Ted Peck built before he passed. This is the upstairs on the left, the downstairs is on the right, and we've got them grouped by county, alphabetical. So it's now a proper library.
Wow.
Andrew, I put a question in the chat, but I'll ask a kind of a follow-up to what you're talking about now. What on campus, is there anything in terms of a fund or an effort to ensure that these are stored long-term? It continue to be stored long-term in the sense of, like, not to be negative, but like what happens after Andrew dies kind of thought pattern, which I know is a long time away. I'm just saying.
No, it could happen tomorrow. I could get hit by a bus, right? Yeah, Corey, that's a fantastic point. So I've been talking with our new dean. He's been the interim dean for a few years, Herman Boyedo, and Dean Boyedo is very supportive of this. He's been instrumental in making a lot of this happen. We've discussed and we've got big plans, but having a permanent location for this is a wish list item for us that we're working towards, and this will take many years, but my own vision for that would be having a soil archive center. Remember, we've got the Mara plots on campus, right? The second continuous study, or the second longest continuous experiment in the world. We've got all the archive soils from the Mara plots there. And I could see there being a soil science education center where we have a proper temperature controlled archive of the original pedons, the resampled pedons, and our Mara plot soils, which go from 1904 to, as of recently, 2 years ago, every 1 to 10 years. We should really capitalize on this. And so there's a lot of institutional support to go towards that. So hopefully I don't kick the bucket before 10 years are up for that to be done. If I do, we do have a really good team of personnel who will keep it going.
So Andrew, this is Bob Miller. So what do you think about the stability of these samples being stored in jars? I mean, I'm thinking here is probably the humidity, in the building changes over time. And granted, those are not perfect seals. I look at air dry soils. I mean, you can have a moisture content of 2%, and you can have a moisture content of 7%. And to me, I'm not saying that it can't be stable. I'm just saying, what do you think about long-term degradation of like the carbon and these kinds of things? And last thing I'll say is it'd be really interesting if you take some of these soils that have been stored 100 years and see what would happen if you wetted them back up again.
Absolutely, Bob. Yeah. So I'm grinning because this is exactly what excites me is how to bring back from the past a lot of the soil microbiome, right? If you were to re-wet these soils from 1861, could you reconstruct the fossil microbiome? I'll begin on that one. So we are working with a few colleagues in the UK at Arizona who are metagenomics folks, and we actually had the Maroplot archive. We got the metagenome sequenced, and so that's currently the work that Alonso Favela, Dr. Favela, is now working on. He's a new professor at the University of Arizona, and we have evidence that there have been shifts in the microbiome assemblage, but the unknown, Bob, is whether that's a function of storage, right? So as you go back in time, changes that you detect in anything are confounded by the storage effects, presumably. There's a few ways around this. For the microbial stuff, that beats me. They've got some tricks up their sleeves that they can use. We've looked at enzyme activities. These are enzymes that exist in the soil matrix secreted by microbes, and we detect pretty high activities of enzymes in these old soils going back to 1904, which is pretty cool. Now, the trick here would be, how do we back correct for changes in total amounts? And for any element that has a gas phase, like carbon and for nitrogen, that's a concern. For phosphorus and zinc, we're not too worried. You can always do a zirconium correction to get the tau normalization. A lot of biogeochemists will normalize a sample like litter of a forest O horizon versus the A horizon. They will normalize a concentration by the tau value, which is thus the zirconium, to account for a bulk density or a fluff change. We could do that here too. We do have some data for the Maroplots and for some of the pedons. That was the Walkley-Black method, or even a permanganate boiling oxidation, boiling a sample in permanganate for 2 days to determine total carbon. So our plan is we have to make two kinds of corrections. First, we have to correct across methods. So we have to reanalyze soils that were originally analyzed for, say, SOC using their method. So that means doing Walkley-Black in the lab, old school style. And we can see by that direct comparison the change in carbon from storage, right? Because if we do the same method as they did in 1904, the delta, which it should be lower for present day, that's what we lost in storage for carbon. The second kind of correction is to convert between the methods. So then converting Walkley-Black to carbon. I know there's lots of conversions out there, but for these specific soils to then do that. So that's for carbon. For things like nitrogen, that kind of beats me. That's going to also have some losses. Again, for PK, the metals, which are lots of our secondary macros and micros, I think we should be okay, thankfully.
Yeah, my thoughts is that I'd like to see how tight those seals were on those jars, because obviously if it's very tight, within a period of time, those soils, even though they're stored dry, they went anaerobic somewhere, after 20 years or whatever.
That's a great point. So a few thoughts here, because we've been working with some nuclear engineers, Bob, to understand radon. So this is actually a rare data set to quantify radon, which is natural. And we have a radon issue for the state in subsoils. The radon is built up in these jars. And when we open up a jar, we can degas it and capture the radon reading. And that's also a proxy of, was it anoxic based on time of storage. I will say that when we processed most of these, we opened up the caps, and a lot of those labels looked like they were done in the 1960s, that they were redone. So I suspect someone in 1960 went through to type out those labels. These are the labels. Let me see if I can go back. These ones in the top left, right? They all have the same label, be they 1904 or 1890. sorry, or 1999. So I think someone had gassed them out when they opened it, but I think you're right. They definitely had moisture, and they have moisture, and they probably went anoxic.
Yeah, cool, cool stuff.
Thanks.
Do you have any free time, Andrew, ever?
Yeah, there's free time to do things. You should ask my wife. She'd probably give you a better answer on that, more objective.
I'll invite her to these, right?
Andrew, I'm not to interrupt that question because I always like to talk about my wife as well, so I get that. But what I'm just kind of curious. So you pointed out some discrepancies in the like phosphorus map, and I suspect also in the K map. What, so since we know that that's there, as agronomists working in Illinois, what do we do with that information right now to help inform our farmer decisions? Nothing? Is there just nothing we can really do with that because it's not at that stage? Or does my question first make sense? And then
Yes, it does. Yeah, I can offer some thoughts, Corey. So first, it's a great question. I think there's two things here. Let's say three things. First two is, what do we do? So first is whether you take the P supply power concept seriously in the first place. And so if you do interpret your soil test P results based upon Chapter 8 of the Illinois Agronomy Handbook, where they give you a different critical value in pounds per acre, depending on what shade of green you fall into on the right-hand side map. If that holds water for you, and if you follow it, then we should think about maybe considering this map right here. If that doesn't hold much purchase for you, that map, then I think this is a non sequitur, and it doesn't really matter. I've talked to a lot of producers, and they don't really seem to follow the map supply power finessing of the recommendation super closely. And I think that's because they're not so sure about the accuracy. So those are the two things to consider. The third thing that I want to point out is, I don't know if we have data to actually support the causal basis of supply power concepts. I know that Iowa and Wisconsin had these in their recs from talking to their state fertility people, and they got rid of it just by virtue of doing some trials to test, maize or corn uptake from a zero check plot. Presumably, you should see more P uptake if you're in the high versus the low supply power region, right? And they didn't see that, so those two states did away with those. So I guess that's the third thing, is that this is a step towards that. The map certainly helps us redraw the lines on the agronomy handbook one, Corey, because the handbook defines this simply based on the lust depth and P content. That's what this soil P map is. But a different question I think we don't have data for in the state is it actually applicable to crop P uptake? I don't have answers there. I'm sure folks like Bob have a lot of ideas on this. I'm a little bit skeptical, honestly. I think it's more complicated than total phosphorus content of loss for how much the crop can drive beyond the top 6 or 8 inches. So if I had to give you a direct answer, Corey, I would say if folks are using the map here for interpreting, I would say, yeah, we know already you want to be cautious, use the map on the left. But I suspect that's a minority of folks based on my discussions with producers.
no, that's a pretty solid reflection. I would agree with.
Cool.
But I appreciate those thoughts. Any other questions? Oh, Georgia asked a question in the chat.
Yep. Are there any plans to update the Illinois Agronomy Handbook based on these updates? Yes, sir. That's the end goal of this. So we've got Chapter 8 needs a lot of updates, right? The critical values are from Lord knows when. We think it's like Bray himself doing this with wheat and open pollinated corn planted in hills in the 1950s is where the data came from those critical values, is what I understand. Obviously, they've been finessed to look at Iowa State's recommendations, so they're probably not super wrong. But we have a parallel project, George, looking at the critical values for P and K, also NREC funded with folks like Dan Schaefer, where we plan to look at soil type specific critical values for the state. And that is going to pair with this mapping approach very nicely to update the maps as well as the critical values. So that will be done, that work, the P&K trials and this mapping work probably by 2028 is an honest answer. I mean, I'm being realistic. By the time that we do all these on-farm trials and crunch the data, yeah.
Think we'd all love to encourage you to do that before 2028 because there's a lot of crop years where farmers may or may not be doing the right thing
Well,
or the most agronomic thing. I don't mean right as in right or wrong.
I should caveat then, Corey. So that's when we'll have the projects ending and we can say, yes, after all of these site years and all of these efforts and double checking, this is what it is. But in the meantime, I think within the first season or two, we'll have a pretty good handle on discrepancies between the maps and the critical value recommendations. And we can provide some updates. So I would say by end of the 2025 or 2024 season, we'll have some basic first steps to communicate to people.
Awesome. Any other questions? Otherwise, I think we can give Andrew his time back. Full 10 minutes of it.
Yeah. Hey, that adds up.